So electric field, first let's understand, or let's try to understand why field is needed. Electric force is like gravitational force, a field force. Remember, in physics, we classify the force into two groups. One of them is contact forces, the other one is non-contact forces. In contact forces, the objects are in contact and they can interact with each other, repel or attract with contact. But for some substances, some forces, for example, like gravitational force, Earth and the Moon, Sun and the Earth, and the planets and the stars, they attract one another, but there is no contact between them. So then we explain the interaction between these space objects by field concept. So the same field concept can be used to explain the interaction between charges, because charges are not in contact. They can attract one another or repel one another without touching or contacting, without contacting with each other. So that's why electric field, this concept is explained or proposed. The concept of field is a model. It's a model. It is not something you can see with your eye. So this is a mathematical model which explains the interaction. That is frequently used to understand how two objects can exert forces on each other at a distance. So we can explain it like this. First, understand this. Electric field or any field. Field is not force. Field is not force. What is field? A positive charge, think about this. A positive charge attracts a negative charge. How? How can we explain this? We explain it this way. This positive charge produces a field around itself. So everywhere around. When another charge enters inside this field, so it will be attracted or repelled. So this positive charge produces a field everywhere alone itself. If when another charge enters inside the field, it will be attracted or repelled. So to define the electric field more precisely, consider a figure on the right here, which shows an object with a small positive charge QO, this is the QO, placed near a second object with a larger positive charge Q. So this is the large one, this is the small one. The strength of the electric field, so the strength of the electric field E, located at this location QO, and at the location of QO, is defined as the magnitude of the electric force. Yes, it is definition of the electric field, but it is not the force itself. Defined magnitude of the electric force acting on QO, but this force will be divided by charge itself. Yes, we are going to say that this positive charge attracts or repels that one with a force F. But if I divide this F by this charge QO, I will get the electric field at that position. So, definition of electric field is force acting on this test charge QO by this big charge Q. First, I will calculate this force, divide this by the charge, and get the field. So, as I said, field is not force. Generally, students are doing this mistake. They think that electric field is a force. It is not. Electric field is a influence of a charge around the space. When another charge enters inside this influence in the area, so then in this volume or the space, then it will be attracted or repelled. So, but the calculation of the electric field can be by force divided by charge. Force on this charge divided by this charge. So is the electric field. Note that this is the electric field at the location of QO, produced by charge big Q. So this charge produces the electric field here. But how can I find it? By the influence of this charge on the another one, by dividing force by the charge itself. So this electric field is not the electric field of Q, it is the electric field of charge Q. So because electric field strength is the ratio of the force to the charge, a sign of the electric field is Newton per Coulomb. Why? Because electric field is equal to F divided by Q. F is Coulomb, Newton. Charge is Coulomb, so unit of electric field is Newton per Coulomb. So electric field is a vector quantity too, because force is a vector. If the force is a vector, if you divide a vector with a scalar, because charge is a scalar quantity, you will get a vector quantity. So then electric field is a vector quantity, because when you divide a vector quantity by a scalar, you get vector. However, when the magnitude of the test charge is great, so this is another thing. So we are going to put here very small charge here, and we will test if here is electric field or not. So by convention, the direction of the electric field at that point is defined as, again by convention, mathematically. This is a exception. We can say that. By convention, the direction of the electric field at a point is defined as the direction of the electric force that would be exerted on a small positive charge, or called test charge, at that point. So then, electric field will be in the same direction of the electric force acting on a positive charge. Now, positive charge, this positive charge repels that positive charge, because the force acting on this positive charge is in that direction. So the electric field at that point will be in the same direction of this positive charge. Negative charge attracts positive towards itself. So the electric field here is towards the negative charge. So then, in general, we can say that electric field of a positive charge is away from the charge. Electric field over positive charges radially. What does radially mean? On the radius, away from the charge. But electric field of a negative charge is invert, which is radially invert, on the radius. Radial. This is important. Next year you are going to use it. Radially invert, on the radius. Radial means on the radius. So this is the electric field lines around the negative charge. This is the electric field lines around the positive charge. So although electric field lines do not really exist, yes, this is a mathematical assumption, it's convention, they offer a useful means of analyzing fields by representing both the strength and the direction of the field. Yes, so this is a very practical way, very useful to understand the interaction between charges. It's a very good method, but don't try to see the electric field lines around the positive charge or negative side. You cannot see them. So, by convention, electric field lines are drawn, directed outward radially from a positive charge in all directions, like sphere in all directions. Note that in this two-dimensional drawing contains only field lines that lie in the plane of containing the point charge. Similarly, the electric field lines for a single negative charge are directed inward towards the charge as shown in the figure. Radially inward in the negative, around the negative charge, radially outward around the positive charge. This is the electric field lines. So another thing we should know is this: if electric field is stronger somewhere, we draw the electric field lines closer. For example, here, where is the electric field lines are closest? Right here, closest. When close to the charge, electric field lines are closer. At the region or the place when the electric field lines are closer, for example here, so many lines are closer. But here, electric field lines are not that. Here is denser, here is less dense. So then, electric field here is stronger than that one. So by looking at the density of the electric field lines, closer if they are, so we say that electric field is stronger. If they are, closer they are, electric field is, but if they are not closer, electric field is weaker. So you can also draw the electric field lines around positive and negative charge. We know that electric field lines are from positive to radially outward from positive and radially inward to the negative. So then we can say that electric field lines start from positive and ends at negative. From positive to negative, you draw electric field pattern in this way. But if you put two positive charge close. In this case, electric field is radial outward from both positive charges. So somewhere here between the charges, there is a place where electric field is 0. So you can find that place. If charges are not equal in magnitude, for example, this is a positive charge with 2q, this is a negative charge with negative q. So this is twice the magnitude of that one. In this case, now how many lines are entering or leaving from q? Count down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 lines are leaving from 2q, but how many is entering negative 2? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, as you see, number of lines leaving 2q is twice the number of lines entering the negative q, because electric field is proportional to charge. So if charge is twice, number of field lines leaving the charge will be twice. If you increase number of charge by 3 times, number of lines leaving the charge will be 3 times. So then number of lines leaving 2q is twice in number than the number of lines entering the negative q, because this is twice the magnitude of that one. So we can reformulate the equation by using the definition of electric field. Now two charges, charge q produce electric field here. Because of this electric field, another test charge experience a force. Also we know by the Coulomb's law what is this force direction. So this positive repels positive in that direction. So electric field of this one will be in the same direction of the force at that location. So definition of the electric field. It says that electric field is the magnetic force, electric force acting on the test charge divided by test charge itself. So the force acting on this charge because of that one, or the force between these two, is equal to, by Coulomb's law, Kc QO divided by r squared. Remember, this is the Coulomb's law. If I write this equation here, Kc QO divided by r squared, divided by once again QO, this 2QO will simplify, and you get the electric field of a point charge at a distance of r. So this charge produces an electric field in magnitude, which is equal to K times Q over r squared. As you see, electric field is proportional to charge. If you double charge, electric field doubles, as we did here. If there is a number of charge, so number of lines leaving the charges, twice number of lines entering the charge. So as amount of the magnitude of the charge increases, electric field increases. But if you take the point away from and choose a point which is farther from the charge, electric field decreases. So distance and electric field are inverse proportional. Even inversely proportional to square of the distance. When the distance doubles, electric field decreases by a factor of 4. So for a positive charge, electric field at the point is outward, radially outward from the charge. For a negative charge, the electric field of a negative charge at the point is radially inward. Don't forget this. So now a question: a proton and electron in a hydrogen atom are separated on an average distance by about 5.3 times 10 to the negative 311, negative 11 meters. What is the proton and electron? The average distance separation between these proton and electron is 5.3 times 10 to the negative 11 meter. What is the magnitude and direction of the electric field set up by the proton at the position of electron? So here, proton's field at the location of electron is asked, electric field. So this is the proton, this is the electron. So electric field at that point will be outside, away from the positive charge. Remember, electric field lines are radially outward from positive charge. But remember again, this is not force, this is the field of discharge at that position. So Proton forms an electric field radially outward from itself. The magnitude of the electric field is equal to kq over r squared. K 8.99 times 10 to the power 9. Q is the charge of proton, 1.6 times 10 to the power negative 19, divided by distance from proton to that point, which is 5.3 times 10 to the power negative 11 meter. So then when you do this calculation, it is 5.1 times 10 to the power of 11 Newton per Coulomb. Section of the question. Find the electric field at a point midway between two charges of 40 times 10 to the power negative 9 Coulomb and 60 times 10 to the power negative 9 Coulomb, separated by a distance of 30 centimeter. Charges are given, Q1, Q2. One of them is, both are positive. And they are separated between them is 30, but we will find at the midway. For that reason, midway will be 15 centimeter from one charge, 15 centimeter from another charge. So then total distance between them is 30 centimeters. So R1 and R2 is equal to each other, 15 centimeters. So the total distance separation is 30. So both are positive charges. Midway. This positive charge produces a magnetic field at the electric field at that point, radially outward. So Q1 of this, Q1 produces an electric field, E1, radially outward. This one also produces an electric field radially outward. But this Q1 produces an electric field here in positive x direction, Q2 produces an electric field in negative x direction. Both are radially outward, but because the positions of the charges are different, their electric field directions are opposite. E1, K Q1 over R1, E2, K Q2 over R2. Because the net electric field must be calculated and resultant, we should apply the principle of superposition. What does it mean? You are going to add these two vectors. You are going to add them in vectors, E1 plus E2. But E1 in positive x direction, I am going to write E1 positive. But E2 is in negative direction, I am going to write it as negative E2. So E1, K, Q1 divided by R1. But R1 and R2 is equal to each other. I am going to say R for both of them. So R is equal to R1 over R2. So K Q1 over R squared is for the E1. K Q2 over R squared is okay for Q2, E2. So what is common here? Kc and R squared are common. So Kc over R squared parenthesis Q1 minus Q2 is the equation for finding the electric field. Remember again, we are going to write here magnitude of the charges, not negative, not negative number, always magnitude. So Q, almost 9 times 10 to the power 9. So R squared, 0.15, square of 0.15. Q1, 40 times 10 to the power of negative 9. Q2, negative 60 times 10 to the power negative 9. So when you do this calculation, answer becomes negative 5 times 10 to the power 3 Newton per meter. What does this negative sign mean? This negative sign indicates electric field is in negative x direction. So this negative sign indicates electric field is in negative direction. So then resultant electric field will have a magnitude 8 times 10 to the power of 3 Newton per meter in negative x direction. So this is the solution of the problem. So when you put a conductor in an electric field, there is a very good and very important thing you can observe. A good electric conductor such as copper contains electrons that are free to move about within the material. Yeah, every conductor has free electrons. They can move from atom to atom. When no net motion of the charge is occurring within a conductor, the conductor is said to be in electrostatic equilibrium. So this electrostatic equilibrium is established in 10 to the power negative 6 seconds. So it takes very short time. The electric field in this case is 0 because all around the charges are distributed evenly. So inside a conductor, electric field will be 0. So electric field is 0 inside a conductor in electrostatic equilibrium, no matter it is charged or uncharged. So for charged sphere conductor, it can be neutral. Electric field inside is 0. If it is charged conductor, say positive, electric field inside again 0, because electric field starts from the surface, not from the inside. So every time inside a conductor, electric field is zero. Never, charged or not, electric field inside a conductor is zero because electric field length starts from surface. But so any excess charge resides on the outer surface of the conductor. It is directed. It's a direct result of the repulsion between the like charges described by Coulomb. So yeah, that's why excess charge, even if you put excess charge inside the sphere or the conductor, they repel one another to the farthest point. Farthest point is the surface, of course. The electric field just outside the conductor must be perpendicular to the conductor's surface. So when you put this electric charge not on a spherical shell, if you put it on a irregularly shaped conductor, so electric field will be strongest at the tip. Here it will be weakest. Here it will be strongest. For that reason, in the thunderstorm, never stay closer to a high point or a tip point, let me say this point, because electric field at that point is stronger, and during the lightning, so lightning first strikes here. So go away from highest points, highest buildings, even go away from the trees, because trees are also behaving this way. So electric field, as I said, inside a conductor is zero. Even the conductor is charged. You can never produce an electric field inside a conductor. And this is very important in electronics, because if you want to protect an electronic device from the harmful electric field caused by some charged particles, you should wound some metal foil around this sensitive device, and you can protect this device from harmful radiation. For example, because of that, when there is a lightning or thunderstorm, if you are driving your car, you are safe inside your car, because your car is conductor, has a surface which is conductor. Inside the car, electric field will be always zero. Even if the lightning strikes your car, you will be safe inside your car.